everybody. Today I want to talk about spanning trees. Okay? Spanning trees. We're gonna build off the idea from what we did last class on shortest path with Dextra. We're gonna build off from this idea. Okay? And we're gonna see how how Dextra could be used, or a variation of Dextra could be used to find a spanning tree. So you might ask, okay, Vito, you're talking about spanning trees, but what are spanning trees? Well, the key word here to note is that they are trees. Okay, they're not graphs, they're trees. They arise from graphs. We build them from graphs, but they are trees, and because they're trees, we know that there are no cycles. All right, and then the other thing that we need to pay attention to, the other keyword here, is spanning. So they do some sort of spanning, or they span or they cover. Okay, so in essence what this means for a graph is a spanning tree covers all vertices with a tree. So it covers all vertices with a tree, which means all vertices are connected and there are no cycles. Okay, so for example, if I gave you this tree here, let's say A, B, C, and then I have D. Okay, and the edges are, say, A to B, A to C, A to D, and B to D. So obviously, this is not a tree, right? Not a tree, because there are cycles. Okay, there's one big cycle. If I were to highlight it, right, this is the cycle there. So I tell you, okay, let's make a spanning tree. Okay, so one spanning tree, it has to be a tree and it has to cover all vertices. So for example, A, B, I'm gonna copy the graph, C, D, right? Would you guys agree that this is a spanning tree? Yeah, it's a tree, right? There's no cycle, so, and I can reach every vertex. Is this a spanning tree here, for example? If I gave you something like this, A, B, C, and D, right? And I asked you, this is not a spanning tree, right? There are two of them there. There's two trees. We're looking for only one. So in this case, we have, oops, I'm sorry. We have not all vertices are connected. Not all vertices are connected. Okay, so in order to make it a spanning tree, I have to either introduce the edge there, or I have to introduce the edge A to B. So I have to pick one of them, right? So another spanning tree, let's see, A, B, C, D, right? This is another spanning tree here. Okay. And I can keep building these, right? Right, I can have another spanning tree that maybe looks like this. I think everybody at this point is, Vito, we got the idea, move on, right? Just in case someone else is still confused, right? This is a spanning tree too. So you see there's a lot of spanning trees, and if you list all of the spanning trees, do you guys know what they are, what we get? So all spanning trees, let's see who can guess. All spanning trees generate let's make this green, a spanning, can anybody guess? Spanning forest. All right, so that's all. I didn't make this up. This is actually a term. Okay. So now comes the question: is if I introduce weights to the edges. So if I say, hey, now there are some weights here. Maybe this costs 1, 2, 1, and this costs 3, right? And if I tell you, hey, generate the minimum spanning tree, and what is the cost of the minimum spanning tree? Okay, usually we're more concerned about the cost, or, well, also the tree, right? So let's see now, what is the cost here of this tree here? We have 1, 3, 1, so the cost is 4. And then we have 1, 2, 1, so the cost is 3, 3. And then we have 3, 2, 1, so the cost here is 6, right? So this here, this tree in the middle, is the cheapest one, right, of 3. In fact, we cannot make any cheaper tree than this. So we need to find a way. So our thing that we need to solve is we need to figure out a way to find the cheapest spanning tree. Cheapest spanning tree. Okay. And we're going to look at 2 algorithms. We're going to look at Prim's algorithm, which is pretty much like dexterous. It's almost identical. Okay. And then we're going to look at Kruskal's. And these are very similar to each other. And Kruskal's is used to generate, you can generate mazes. In assignment 10 that you guys are not going to do, you were going to be asked to generate a maze using Kruskal's algorithm or some other algorithm, but you're not doing assignment 10, so you won't have to do this. But so technically we don't have to cover spanning trees, but still they're not easy to do, and you know, you'll see them up eventually in probably algo and data structures when we take it later on. So this is all fine and great, but you know, you say, Vito, you didn't tell us about where can we use this. Well, the thing that comes to in mind, or that's also in the notes, is if these are, for example, you know, houses. These are all houses, and then we need to run. They're connected in many different ways. So, for example, let's say I have a neighborhood. I have A, B, C, D, E, and F, and there are streets between all of the houses. This is in suburbia somewhere, right? So maybe we have something like this, and Comcast comes around and says, hey, Comcast says we need to run coaxial cable. We need to run cable underneath every road in the neighborhood to install internet, right? And they say all the houses have to be connected. Maybe they're, you know, gamers living in the houses or whatever. People like to play games. So Comcast has to determine what's the cheapest way to do this, and say, hey, from A to B, to install a cable between A and B, is going to be very cheap. It's going to be maybe just 1 unit of cost. But, you know, between B and C, maybe there's some neighbor living there that they don't like digging. They don't, you know, maybe there's a fountain in the middle here. Maybe, you know, there's some certain costs associated with. So installing a cable between B and C might cost 5. So all of these roads here, you know, they have something like that, certain costs associated with digging underneath them. And now Comcast has to figure out, all right, why don't you give me a configuration where we need to dig, so it's the cheapest way to do this, right? So if I look at this, it seems like A to B is pretty cheap, A to D is pretty cheap, also D to B is pretty cheap, but I already have B. Let's see what else. Then B to E is pretty cheap. I can do that. And then B to F is pretty cheap. And now let's see. So do you guys see what I'm doing? I'm always picking the cheapest edge. It's kind of an greedy algorithm, and that's how it works. You know, you always pick the cheapest edge and to connect two houses, right? Because if you can find the cheapest way to connect them, why not, right? If I can see A to B, it's only costs 1, let's go ahead and do it. We can't do anything cheaper between A and B. A and D, that's the cheapest, right one, so let's go ahead and connect them. So let's see, the only one that's not connected is C, right? Everything is connected besides C. So the cheapest way to get to C from the things that I've already connected, I can do 6 or 5, or I can do 7. So let's go ahead and pick this one here. So the total cost at this point for Comcast to do this is 1 plus 1 plus 1 plus 5 plus 2. So total cost we get, let's see, 1 plus 1, 3, 5, total cost of 10. And you can go ahead and try to see if there's any other way to do this cheaper. Maybe there's a different configuration, but I doubt we're going to get a cheaper cost than 10. Okay, so that's the motivation behind it. Another example might be the letters here, A, B, C, D, E. Maybe all of these are your friends, and you want to kind of broadcast a message to all of your friends, and you want to find the cheapest way. If I tell one of my friends the message, maybe they'll charge me less money than some other friend, but essentially I want all of them to know about my message. So the idea is, okay, how do I circulate the rumor, or how do I circulate the message to tell everybody what will be the cheapest cost to do that. All right, I hope this made sense. These are what spanning trees are. In the next video, we'll look at an example and go through it and see